This word diffusion, okay, in context of gases, means that a gas spreads out uniformly through another gas. So when you think about things that you smell, okay, this is one of the easiest ways to think about this. When you think about things that you smell, those compounds that are odors are gases, and they are moving through the air in the room and then hitting your nose, and you are then smelling them, okay? So when you think about things that you can smell, here's just some examples, right? Y'all know the smell of a Christmas tree, a pine tree, right? The smell of apple pie, the smell of fire, the smell of when it's going to rain, right? That smell in the air, that's actually ozone is the compound that we're smelling, one of the compounds. But so diffusion means that a gas will spread out and fill up the space that it's in. It'll mix with the other gases in the space. But does it move directly from here to there? Like, some of y'all can smell this candle now. It's not lit. Some of y'all might not even be able to smell this at this point. It's just open here and there. This is a big room. There's a lot of space for these scent gases, these odors, to move through. What could I do to make you guys smell this faster? Yeah, I could do a temperature change. I can heat this candle up. And then what's happening to the gas odors? Yeah, their speed is increasing. So they're moving faster to fill up this space, but they're still not moving straight line from me to you. So as they're moving through the air or through the space, they are moving chaotically. Okay. They are trying to move in a straight line, but they keep running into what? Other gas molecules. And they hit those other gas molecules and they bounce off. Right? That's diffusion. Eventually, would this entire green gas and this entire red gas both mix up together? Yes, absolutely. Okay, that's diffusion. Eventually, this candle scent will fill the whole room. And then it will continue to spread out into the atmosphere until we don't smell it anymore because it's too diffuse. But that's diffusion, okay? The other word you need to know is effusion. It's a different word. Diffusion means one thing. Effusion means something else. Effusion is a gas or gases in a container escape or pass through some kind of small hole. That is what effusion means. It's when a gas escapes through a small hole. And you can think about this like a hole in a balloon, right? Okay. You know, I hate balloons. I hate balloons. I don't like anything about them. I'm going to try. Got some tape on here, right? I'm going to try to do the thing where I poke a hole in the balloon, but through the tape, so it doesn't actually pop. This isn't sharp enough. Okay, good. It's not going to work. Yay, I don't have to do it. Did you get the idea? Maybe, I hope. You got a little hole, gas can escape. But if you have a mixture of gases, which one is going to escape the fastest? The smaller ones. Smaller gases escape faster. That's the main thing. Sometimes we can calculate the ratio of escaping, okay? Graham's law of effusion. All right. This should also be a formula on a useful equation sheet, the useful equation sheet that I gave you. But basically, it says the rate of effusion of gas A in your mixture divided by the rate of effusion of gas B. So we're doing a ratio, yes? We're finding a ratio. This ratio is calculated by taking the square root. But look, molar mass of gas B. See how it's, you gotta remember that, okay? Molar mass of gas A on the bottom of the calculation, okay? So typically when you read a problem, it will say calculate the ratio of gas, first one. That would be your top one. The first one listed. Ratio of this gas to this gas. That's how you know what goes on top and bottom when you read the problem. Of gas A to gas B, top, bottom. So look at this example. Let's calculate one real quick. How fast? Or calculate the ratio. I think this should be number 30. No, we're in the 30s now. Number 31. Okay. Calculate the ratio of effusion rates of CO2 and SO2. Of CO2, gas A. And then SO2, gas B, the second one listed. Okay. So we're seeing how fast CO2 is escaping compared to SO2 ratio, this compared to this. So all you need are the molar masses. That's all you need to do this math. You just need the molar masses, okay? I gave you these two values here. These are only taken to the 10th place as opposed to the 100th place, which is what I normally like to do on our molar masses, but whatever, that's fine, okay? You need the molar mass of CO2 and the molar mass of SO2. That's what you need. And then we're going to do what? Divide and square root. Now you got to remember which one goes on top and which one goes on bottom in our calculation. So we're doing the rate of which gas first? We're going to do CO2 first. Which one do you expect to escape faster? Just looking at the molar mass, SO2. Just looking at the molar masses, which one do you expect to be escaping faster? CO2, because it's the lighter of the two. Yeah. So let's see if we're right. Take the square root. Remember, what is the molar mass on the top under our square root? B, gas B, gas B. So we're going to do 64 point, what is it? 1. That's what I said on the slide. Let's do that. Divided by 44.0 grams per mole. And just remember your answer, you can think about whatever calculator answer that you get, right? This number right here. It is a ratio. It's that number to 1. That over 1, okay? What does that mean? CO2 effuses 1.21 times faster, right? This is a rate. It's 1.21 times faster than SO2. This would be a very common kind of multiple choice question, right? where the answer would be a statement like that. CO2 effuses 1.21 times faster than SO2, right? That's the kind of sentence statement that would describe that mathematical answer. Make sense?